Today I'd like to go over some other wave properties with you. And the two properties we want to talk about today are amplitude and frequency. Amplitude, we've already talked about, is how high a wave is. You can see the red has a higher amplitude than the green. And what amplitude means for sound is how loud the sound is. If I talk really quietly, the sound wave would have a low amplitude. If I talk louder, the amplitude is going to be much larger. Amplitude tells you how loud a sound is. It tells you how bright a light is. So a higher amplitude will be brighter than a lower amplitude. And that's what amplitude tells you with sound and light. Frequency, you can see the green one has a much higher frequency than the red. And what frequency of a sound wave tells you is what note you're playing. So for instance, I have on my iPhone an app that lets me generate any frequency I want. This is 261. This is 1060. And you can hear the difference between those two. Frequency, again, tells you what note, and the amplitude tells you how loud. Okay? With light, frequency tells you what color or type of light you're dealing with. So let's go back to sound frequencies again. And I'd like you guys to take a moment to draw out a piano that looks similar to this. And I'd like you to be able to identify what frequency would produce each of the different notes on the piano. I don't have a piano, but I do have my guitar, and each string should be tuned to a different note, meaning each string should have a certain frequency. When you're looking at your piano, the place where you want to start is where you have the two sharp or minor keys, and you want to go right to the left of that, which would be this key right here, and hopefully you know that that key is C. So on your piano that you drew, on this key that's right next to the two sharp keys, label that C, and if that's right in the middle of the piano, it's called middle C, and that key should be attached to a string that will produce a frequency somewhere around 256 hertz. The key right next to that is D, and that'll be 288. And then E, 320. F, 341.3. G, 384 hertz. A is 426.7 hertz. B is 480 hertz, and after B, we're right back to C again, and it's 512. This gap is called 1 octave, and what I'd like you to know about an octave is anytime you go up 1 octave, it should be double the frequency. If you go down an octave, so I go to this C, that should be 128 hertz. If I take this B right to the right of the three black keys, that would be this one here. That's my next B. It should be double that, which would be 960 hertz. Something else I want you to know about frequency is that we can't hear all frequencies. There's a range of frequencies that we can hear, but there are frequencies that are too low for humans to hear and too high for humans to hear. So if you look at the human range, it's somewhere between 31 hertz and about 19 kilohertz. Any higher than 19 kilohertz, we can't hear it anymore. That's called ultrasound. So when you hear somebody refer to ultrasound, it's a sound that's such a high frequency that we can no longer hear it. And you'll notice this one is at 22 kilohertz. We can't hear that anymore. Just because we can't hear it doesn't mean that things like a raccoon or a cow can't hear it. They can. They have a range that extends further than human hearing. There's also on the other end frequencies that are so low, such as this one, that humans cannot hear, and they are called infrasound. So ultrasound is when it's too high a frequency, and infrasound is when it's too low of a frequency. You'll notice things like elephants can hear sounds that are much lower frequency than we can. And you'll see things like dolphins and porpoises can hear much higher frequencies than we can. Just like with sound, light has frequencies that tell us color or type. So you should have your reference sheet. It should tell you the frequencies of all the different colors we can see, as well as things like ultraviolet. That's a frequency higher than violet. We can't see it, but it's still there. Some creatures can see ultraviolet. Same thing on this end. Less than red is called infrared. It's still light, still travels the same, still works the same. It's just the human brain is not sensitive to those frequencies. Radio waves, microwaves, X-rays, gamma rays, we cannot see those either because of frequency. So frequency tells you the color or type of light, and frequency tells you the note or the pitch of a sound. Okay, when you guys looked at your relationship between speed and wavelength and frequency, you should have found the following relationships. You should have found that higher speeds give you a higher wavelength. In fact, it's proportional. So if you double the speed, you should double the wavelength. Why is that? Well, if we look on Desmos, you can see the waves being produced. And what we're going to do over here is change the speed. So right now we're set at a speed of 5. We're going to pause it. We're going to reset our time to 0, and we're going to double the speed. Now when we look, these waves are traveling faster, so they can get farther away before the next wave is produced. It makes a bigger gap. A higher speed gives the wave more time to escape before the next wave is released. This time, instead of showing it as a circle, we're just going to have it like a little bowling ball or something. And we're going to release lots of bowling balls. And if they're moving slowly, the bowling balls are going to be close together. This next time, we're going to have it move at a faster speed. And that will give the first bowling ball more distance before the next bowling ball is released. It's moving faster so it can get farther away before the next one is released. I'm going to make it even faster. And you can see how far apart they are. If I double my speed, I double the gap between the bowling balls. Or in this case, I double the distance between the waves. I double the wavelength. Then you did wavelength and frequency, and this time you found just the opposite. You found an inverse graph, which meant higher frequencies made less wavelength. If you look at it again on Desmos, we're going to keep the speed constant and we're going to change the frequency. So this is what it looks like originally with a frequency of 2. Now we're going to make our frequency 4. And actually I lied, we're going to bring it all the way up to 8. Much higher frequency. And you can see the gap is much smaller. A higher frequency, they don't have a lot of time to get away before the next wave is made. There's less time in between wave creation, so there's less of a gap. Again, showing it as bowling balls, we're not going to change how fast they're moving. Instead, we're going to change how quickly we release them. We start out kind of slow with a frequency of 0.5. Now we're going to take the frequency and we're going to double it. And you can see they're now closer together than they were before because they don't get very far before we release the next wave. We're going to bring it up even higher. And you can see the gap got much smaller. So higher frequency, less distance between the waves. This is the summary of what we should have gotten in lab. We should get a relationship that says wavelength, that's how far the waves are apart, is equal to the speed of the waves divided by the frequency. Okay? So I'd like you guys to get all your notes from today, share a picture of your notes with me, and answer some questions on the Google form. This will be due Thursday at midnight. So you have Wednesday to copy your notes, Thursday to do the Google form, and then get it all turned in to me. If you have any questions, do not hesitate to reach out and ask.